So in previous videos we've seen this I/O abstraction, right? So values of type IOA represent a computation, sort of a first-class imperative program that can do some I/O, like it could print stuff on the screen or read something from the network, and then eventually, when it's done, is going to return a value of type A. And we saw that I/O is a functor and an instance of applicative, and that applicative instance in particular allows us to compose I/O computations using the applicative interface. And so we can use that to put smaller I/O computations together into bigger ones. So we have things like pure, and then in particular this app operator is really what lets us do composition, where if we have two I/O computations, we can compose them together into a bigger one that runs both and then combines their outputs, in this case by applying the function output by the first one to the value output by the second one. And then we get other things that we can derive from that, like this and then operator. We also get things like traverse, where we can do a whole bunch of I/O actions on a bunch of things in a list, or even on trees and other things, as we saw in another video. So the thing is, though, it turns out that this is not enough. There's some things that we might want to do with I/O, certain ways we might want to compose them, that we cannot do using the applicative interface alone. So as an example, so here's an example that we can't do using only applicative. I want to write a program that will print or prompt the user for their name. It will read the name that they type and then greet them by name. This seems pretty straightforward, something that we could very easily write in Java or Python. I claim that we cannot actually do this using the applicative interface of I/O. So let's try it and see why we can't do this. So we'll call it greet by name. And so this whole thing should just be a computation of type I/O unit. That is, like, the whole thing as a whole is not going to return any result at the end. It's just going to do some stuff. It's going to print something on the screen, and then it's going to wait for me to type something and read it in, and then print something else out on the screen, right? So how do we implement this? So we can first, of course, prompt them for their name. That's easy. We can say put Sterling. Actually, let's just do put str. What is your name? So put str, of course, doesn't add a new line on the end of the string you want to print out. So after it prints this string, it'll just be sitting there waiting for us to type something, with the cursor positioned on the same line. Okay, and that doesn't return anything, and that's fine. So I just want to say, and then I'm going to do get line. Right, get line will return a string. And then I want to do something like put Sterling greetings, and here's where we start to see the problem. I want to greet them by name, so I want to take whatever they entered here and stick it in this string here. And the question is, how do I get access to that? So obviously doing this and then operator is not going to work, because this explicitly ignores the value returned by this. Okay, so that's not what we want to do. So let's think about, so there's something else we could do. So I don't just have to use this and then operator. I could generally use this app operator, and I could combine them with some function, right? But that doesn't do it either, right? Because this, if I put some function here, that allows me to combine the result of this computation and the result of this computation. But I don't just want to combine their results. I mean, in fact, this thing doesn't return an interesting result at all. I want to take the result of this one and use it in this one. And it turns out that applicative can't do that. So if we look at the type of the app operator, right, there's no way for this computation to depend on the output of this one. Like, we can take the output of this and the output of this and combine them, but I want the actual effect that this thing does, right? In this case, what it prints to the screen, I want that to change depending on what the output of this thing is. And it turns out this is a fundamental limitation of applicative, that subsequent computations cannot depend on the results of previous computations. In other words, the choice of which computations I'm going to run is fixed from the very beginning of the program and can't change depending on intermediate results. Sometimes this is really nice, and when you can get away with it, it's great because it means you can do things like statically analyze and optimize your program so you know exactly what actions are going to run before the program even starts. And you can use that to optimize some things and analyze it in various ways. But obviously in other scenarios, it's pretty limiting. So this same kind of limitation comes up when we're doing other things too. So for example, on the homework you're looking at parsers, and you can get very, very far with applicative. Plus, if you have alternative, which you're looking at on the homework, there's a whole lot of parsers that you can write. In fact, most kind of parsers that you would write to parse a programming language, you can get away with just applicative and alternative. Alternative basically lets you say have a limited number of choices of things you can do. So depending on what you see, you can choose one of a number of alternatives. However, there's other types of formats. For example, it's very common in a network packet format to have something like, well, first there's going to be say a 16-bit field with a number, and that number tells you how many more bytes you should expect to see in the rest of the packet, for example. And it turns out you cannot do that using just the applicative instance for parsers, because you need to say first parse a number, and then depending on what number that is, I'm going to run another parser a certain number of times. And there's no way to do that using only applicative. Another example would be, if with the state computations that we've seen, what if we want to decide what to do based on the current state? So for example, we want to add up some numbers in a list, for example, except if the sum gets over 1,000, then we want to stop early and just return for that first number that was over 1,000. Again, you can't do that using applicative. You can try, and you can see why it's actually not possible to do that. So we want, so this can't be done. So I'll comment this out. We want a way to compose two actions such that the second action can, or I guess I keep using the word, I was using the word computation before. I'll stick with that word. You'll sometimes hear the word action as well. Two computations such as the second computation can depend on the result of the first. Okay, so in other words, we want something, so again, it's focusing on I/O, we want something kind of like this. We want to be able to take some I/O computation that returns an A, and then I want to be able to give a function, right, that says, I'm not just giving you two computations, I'm giving you a first computation and then a function that says, if you tell me what the result was of the first computation, then I'm going to tell you what computation to run second, right? But this thing can now specifically depend on this A value. And then ultimately what we get, when we compose these two, the whole thing is an I/O action that returns a B. And what it does is it's going to run this and then take the output from it and feed it into this function to decide what to run second, and then run that. And then finally it'll return whatever that second thing outputs. So it turns out that there is an operator that does this, and it is written like this. And any applicative functor that additionally supports this operation is called a monad. And we'll look more at monads in general in the next video, but for now let's just see how we can use this operator to do this example that we wanted to do with I/O. So I can now say greet by name. So we still want to do this first. What is your name? I can still say and then, because I don't care about the output of this. Now what I'm going to do is I'm going to say get line, and I want to compose this with a second computation, but I want to compose them using this operation because the second operation that I do is going to depend on what getLine, the result that getLine returns. So I'm going to say this. By the way, this is pronounced bind. is the bind operator. So I'm going to bind it, and then I need a function from, in this case, this returns a string. So I need a function from string to IO. Actually, it's going to be unit, right? Because I want a unit at the end here. So we'll just say, let's take the string s, and now I need to return an IO computation, and the IO computation I want says put strlen greetings s. Right, now I have access to this s, which was the output from this previous computation. That's exactly what I wanted before. Okay, and then I use that s to make this string, which is actually going to get printed in this section. Do I need one more parentheses? Yes, I do. Okay. Some of these parentheses, it turns out, are unnecessary, but leave them all in for the moment. Let's just try this out and see that it works. So make this bigger. Greet by name. My name is Dr. Yorgi, and it greets me.